2. Data organization. The data folder neatly organizes the raw dataset, exported images, and process training splits, which is crucial for reproducibility. 3. Model files. Keeping base model.py and ResNet 18 model.py alongside saved models .h5, .keras, and web model allows for both experimentation and easy web deployment. 4. Results folder. Clear separation of logs, Grad-CAM outputs, misclassified images, and training plots makes it easier to analyze and debug model performance. 5. Scripts folder. Essential scripts for data handling, training, visualization, and conversion to TensorFlowJS are logically grouped, improving maintainability. On image upload. Currently, without user-uploaded image support, the application primarily displays results from predefined datasets. This simplicity reduces server load, ensures consistent performance, and aligns with your current goals of avoiding back-end complexity. However, allowing image uploads could 1. Engage users. Users could test the model with their own data, making the tool more interactive and relevant. 2. Expand use cases. This feature could simulate real-world scenarios, enhancing educational value and potential research applications. 3. Feedback opportunities. User-uploaded images might uncover edge cases or inaccuracies, offering valuable feedback for model refinement. If bandwidth or computation is a concern, you could restrict image size, limit uploads to small image dimensions, and enforce file type constraints. Client-side validation. Perform basic image pre-processing directly in the browser to reduce server load. Would these benefits and mitigations sway your preference toward implementing an upload feature?
Yeah, I'm not sure. We might leave it open for now. Well, because we still have to train the model.
It makes sense to leave the image upload feature open for future consideration, since your primary focus right now is training and improving the model. Given your current progress and the project structure, I recommend focusing next on the train.py script. Why train.py? 1. Core pipeline. It defines the training process, which is the backbone of your project. Refining this script ensures you have a robust model to work with. 2. Result outputs. This script determines how well the model performs and generates outputs like training plots, Grad-CAM visualizations, and logs. 3. Next steps alignment. After training, you can focus on integrating the model into the web interface, index.html and main.js, or exporting it for web deployment, convert to tfjs.py. Once train.py is finalized, validate the training pipeline with the dataset. Dataloader.py may need tweaks if issues arise. Use visualization.py to refine performance outputs like plots or Grad-CAM heat maps. This flow ensures a clear progression toward model deployment while keeping the front-end integration ready for when the model is trained and tested. The provided train.py script is designed to load the BreastMNIST dataset, pre-process it, train a simple convolutional neural network, CNN, and save both the results and the model. Here's a summary. 1. Dataset loading and pre-processing. The script loads the dataset from a .npz file, normalizes pixel values to a 0-1 range, and reshapes the data to include a channel dimension. It also handles class imbalance by computing weights for each class. 2. Model definition. A CNN with 3 convolutional layers, max pooling, and dropout is defined. The model is compiled with the Atom optimizer, binary cross-entropy loss, and metrics including accuracy and AUC. 3. Training process. The model is trained for 15 epochs with a batch size of 32, using early stopping and checkpoint callbacks to save the best model. 4. Results visualization. Training and validation accuracy and loss are plotted and saved as PNG files for performance review. 5. Evaluation. The script evaluates the model on a test set, calculating metrics like test accuracy and AUC, and saves these results to a JSON file. 6. Model saving. The trained model is saved in both .keras and .h5 formats for future use. This setup enables a straightforward end-to-end pipeline for training and evaluating a simple CNN on BreastMNIST data, with results ready for visualization and deployment. The train.py script in its current state is functional, but requires some adjustments and clarifications to ensure it runs seamlessly and aligns with your goals. Here's a practical assessment. What will work? 1. Data loading and pre-processing. The dataset loading and normalization steps are straightforward and should work if the BreastMNIST 224.npz file is properly formatted and available at the specified location. 2. Model definition. The CNN architecture is simple and should compile without issues. It is suitable for initial experimentation. 3. Callbacks. Early stopping and model checkpoint callbacks are well implemented and will help manage training efficiency and save the best model. 4. Visualization. The training and validation accuracy loss plotting is correctly implemented, providing insights into the model's learning process. What needs further modifications? 1. File paths. Ensure all paths, e.g. to the .npz file, output directories, and saved models exist and are accessible. The script assumes a specific directory structure. 2. Hyperparameter adjustments. Default values for epochs, batch size, and learning rate might need tuning for optimal performance. You should also test with a smaller dataset subset to verify functionality before full training. 3. Error handling. Add checks to validate that the dataset is properly loaded and contains expected keys and shapes. This ensures the script doesn't crash if there's an issue with the data. 4. Logging. While some results are saved, additional logging for metrics like confusion matrices or Grad-CAM visualizations could make the training process more informative. 5. TF.js conversion. Ensure the TensorFlowJS converter process works as expected, and address issues like duplicate weight names or version conflicts. Optional enhancements. 1. Class imbalance handling. While class weights are computed, you might consider oversampling or data augmentation techniques for the minority class. 2. Scalability. If you plan to add more complex models later, modularize the code to easily plug in other architectures, such as ResNet. 3. Testing. Include a smaller test case to quickly validate the training pipeline without consuming excessive resources. With these adjustments, the train.py script will not only run as intended, but also be more robust and adaptable for future iterations. The updated training script includes several improvements to make it more robust and user-friendly. Firstly, I added error handling to ensure the dataset exists and contains the expected keys before the script runs, preventing crashes due to missing or incorrect data. Secondly, I implemented handling for class imbalance using the compute class sort weight function to dynamically calculate weights for the classes based on the dataset distribution, which improves training fairness for underrepresented classes. The code structure has been modularized by introducing a function to build the model, making the script cleaner and easier to maintain or adapt for different architectures. Training metrics such as accuracy and loss are now plotted and saved as images in a dedicated results folder, allowing for better tracking and analysis of the model's performance over time. Additionally, test performance metrics like accuracy and AUC are saved in a structured JSON file for future reference. The script dynamically creates directories for storing models, plots, and logs, ensuring that output is well organized and does not overwrite existing files. The updated code also logs training progress and outputs useful debugging information at every stage, such as data shapes and class weights, making the training process more transparent. These changes collectively enhance the script's usability, reproducibility, and readiness for deployment.
Okay, so we did another training. Here we get to a pretty high accuracy. So area under the curve of 0.9. Validation loss of 0.6 seems a bit high. Can you explain the output?
The training output shows significant progress in terms of accuracy and AUC, but there are a few points to address regarding validation loss, model performance, and possible areas for improvement. Summary of results. 1. Training progression. Accuracy increased steadily, reaching a high value of around 92% by the final epoch. The AUC, area under the curve, also improved significantly, indicating better discrimination between the two classes, peaking at top 0.97. 2. Validation metrics. The validation loss improved early on, but plateaued after epoch 10 and even increased slightly towards the end. Final validation accuracy was 87.18%, and AUC was 0.92, showing good but not perfect performance. 3. Test set performance. Test accuracy. 83%, and test 8.89 are reasonable and suggest the model generalizes fairly well. However, the higher validation loss relative to the training loss, 0.69 validation loss versus 0.36 training loss, may indicate slight overfitting or noise in the validation set. Key observations. 1 validation loss plateau. The validation loss did not improve beyond epoch 10 and even started increasing slightly. This could indicate overfitting to the training data or a need for further tuning, such as regularization adjustments. Increase dropout or add L2 regularization. Early stopping. Consider halting training earlier to prevent overfitting. 2. Validation accuracy versus loss. The validation accuracy and AUC are quite strong despite the validation loss being higher. This discrepancy suggests that while the model is correctly classifying examples, its confidence in predictions might vary, which is reflected in the higher loss. 3. Test metrics. Test accuracy, 83%, is lower than validation accuracy, which is expected but suggests that the model could still benefit from more generalization techniques, e.g., better data augmentation or additional validation. 4. Training and model saving. The training results were successfully logged and plotted. The model was saved in both H5 and Keras formats. The warning about the HDF5 format being deprecated in TensorFlow 3 is informational and doesn't affect functionality, but suggests switching to the native Keras format in the future. Next steps. 1. Focus on validation loss. Review potential sources of noise in the validation set or consider adjusting the train val split. Explore additional regularization techniques or hyperparameter tuning to balance training and validation performance. 2. Evaluate Grad-CAM visualizations. Generate Grad-CAM heat maps for test or validation samples to verify that the model is focusing on meaningful regions in the images. 3. Data augmentation. Confirm if further data augmentation might benefit generalization, particularly for minority classes. 4. Hyperparameter tuning. Experiment with learning rates or batch sizes to refine performance further. 5. Compare to baselines. Use a simpler model like ResNet 18 for comparison to understand if the custom model is optimal or if a pre-built architecture performs better on this dataset. By addressing these steps, the model can be further refined for better generalization and reduced validation loss. The graphs show how training and validation metrics evolved over 15 epochs. 1. Training versus validation accuracy. Training accuracy steadily increases, peaking near 0.92, showing the model is learning the patterns in the training data. Validation accuracy rises initially, but fluctuates after epoch 10, suggesting potential overfitting as the model becomes more specialized to the training data. 2. Training versus validation loss. Training loss steadily decreases, indicating the model is minimizing errors on the training set. Validation loss shows a general downward trend, but rises slightly after epoch 10, reinforcing overfitting concerns or noise in the validation set. The increase in validation loss, while accuracy remains high, suggests that while the model can correctly classify samples, its predictions may lack consistent confidence. To improve generalization, consider tuning regularization parameters, adjusting data augmentation, or implementing cross-validation. This table compares various models and methods on the BreastMNIST dataset in terms of AUC, area under the curve, and ACC accuracy. 1. ResNet 18, 28 achieves the highest accuracy, 86.3% among the listed models, with an AUC of 0.901. 2. Google AutoML Vision has the highest AUC, 0.919, but a slightly lower accuracy, 86.1%. 3. ResNet 50 models, while more complex, perform slightly worse than ResNet 18, suggesting diminishing returns with increasing complexity for this dataset. 4. Simpler automated solutions like AutoKeras and AutoSclern underperform compared to manually tuned ResNet models. If accuracy and AUC improvements are needed, ResNet 18, 28, or Google AutoML Vision are good references for potential targets. However, consider simplicity and computational efficiency when deciding on the next steps. The model in the train.py script is a simpler convolutional neural network, CNN, compared to ResNet 18 or Google AutoML Vision. Here's a comparison. 1 architecture complexity. Train.py model consists of 3 convolutional layers with 32, 64, and 128 filters, each followed by max pooling layers, and 2 dense layers, one with 128 neurons and 1 output layer with sigmoid activation. This makes it a lightweight model with significantly fewer layers and parameters than ResNet 18. ResNet 18 features 18 layers, including residual blocks, designed to overcome vanishing gradients and learn deeper hierarchical features. ResNet 18 has a much larger number of parameters, making it more complex but more capable of capturing intricate patterns. Number 2, performance. The train.py model achieves a test accuracy of 83% and a test AUC of 0.89 after training. While reasonable, it does not match ResNet 18's AU of 0.901 and accuracy of 86.3%. ResNet 18 generally performs better, as seen in the table, especially for high-dimensional image data like BreastMNIST. 3. Flexibility and scalability. The train.py model is simpler and faster to train, but may not generalize as well or achieve as high a performance as ResNet 18 due to its limited capacity. ResNet 18 is more scalable and better suited for tasks requiring high accuracy and robustness, but it is computationally more demanding and might not be ideal for quick experimentation or deployment on resource-constrained environments. 4. Model size. The train.py model is lightweight, with smaller file sizes for trained weights, in the range of 134 megabytes. ResNet 18 has a significantly larger size, typically around 44 megabytes for the weights alone, but would increase when fine-tuned for a dataset. Conclusion. The train.py model is a good starting point for simplicity and efficiency. However, if higher performance is critical and computational resources permit, integrating ResNet 18 or a similar architecture could provide better results. That said, the decision to move to ResNet 18 should balance training time, complexity, and performance gains.
I don't know, to me it looks like it's doing quite well as it is. So it is a much simpler, so 3 convolutional layers instead of 18 in ResNet 15. So interestingly enough, like adding more layers doesn't improve performance. So ResNet 50 actually had the slightly increased performance. Yeah, so our performance at the moment is actually fairly close to ResNet 50. Interestingly, the number of pixels doesn't make a difference. I mean, surely you have more resolution in the image, you should get better performance. So my hypothesis will be that with 224 by 224 pixels, you can achieve even higher performance, going to 0.99 and so on and so forth. But the current results didn't show that. Does it happen for all datasets as well? Yes, some of them are a bit oversaturated as they are. Yeah, maybe you can explain in relation to the other datasets, training on the other datasets as well in the table provided. But yeah, to me, yeah, please convince me otherwise, but it seems like our performance is actually better than considering how much simpler the model is, so relatively the performance is better. So essentially there is, can you talk about the bottleneck, the threshold of the number of layers? So obviously it seems like more layers doesn't mean better results. What do you think?
Your observations are quite accurate. The number of layers alone doesn't guarantee better performance, as shown by the comparison of your simpler CNN with ResNet 18 and ResNet 50. While ResNet 18 and ResNet 50 have deeper architectures and are better at capturing complex patterns in larger datasets or more diverse features, your 3-layer model performs impressively on BreastMNIST, given its simplicity. The diminishing returns on performance with increased resolution and complexity might indicate that the dataset is already well represented at 224 by 224 pixels, and the model's capacity is sufficient to capture the necessary features. In datasets like BloodMNIST or PathMNIST, this might be different, as they seem to saturate at higher resolutions with more complex models. It could be beneficial to train your current model or ResNet 18 on other datasets from the table to see if similar trends persist. This insight can be a great addition to your HTML documentation, as it would contextualize your model's effectiveness relative to complexity and dataset characteristics. Would you like to focus on training other datasets next, or refine the explanation for the current model's simplicity and its relative performance?
So there's a couple of things in training. During training, what are we saving in terms of results? Okay, can we update the HTML to show something more meaningful? But yeah, we would like to display the current accuracy loss PNG that we have saved, and the logs. We have a metrics JSON file in the logs as well. So we need to update the HTML because currently it's not displaying anything. Or what else? We have some of the other files missing, files and folders. I'll share the structure of the project again, an updated structure of the project, files and folders.
Here's a breakdown of what's going on and suggestions for next steps. Current status. 1. Model location. Your model's directory contains placeholders, base model.py, ResNet 18 model.py, etc. But the actual trained models, best model.keras, BreastMNIST model.h5, are in the scripts models subdirectory, which is unusual. The trained models should ideally reside in the top-level models directory for consistency and clarity. 2. File sizes. The best model.keras file is 128 megabytes, which is expected for a model with multiple convolutional layers and dense connections. However, the size might seem large because it includes both architecture and trained weights. Empty folders like web model and placeholders in misclassified images should be populated or removed if unused. 3. HTML and JavaScript linkage. The index.html file is correctly linking to main.js for dynamic updates, but main.js is currently empty. This explains why the page doesn't display any dynamic content or plots yet. 4. Metrics and plots. The training results, such as metrics, from metrics.json and plots, e.g. accuracyloss.png, are generated, but the HTML page doesn't yet fetch or display them. Grad-CAM related folders, Grad-CAM heat maps, misclassified images, are either empty or unlinked in the front end, leading to gaps in functionality. Suggestions for next steps. 1. Organize the model files. Move the trained models, bestmodel.keras, BreastMNIST model.h5 from script/models to the top-level models directory. Update any scripts that reference these paths. 2. Populate main.js. Implement JavaScript to dynamically fetch and display metrics, plots, and Grad-CAM heat maps, as outlined in the earlier response. This will bring your index.html to life.
Give a summary of what we did today.
Today, we focused on refining the BreastMNIST visualization project, addressing folder structure issues, updating the index.html file, and ensuring alignment with the newly structured files and folders. We also reviewed the integration of metrics, plots, and Grad-CAM visualizations dynamically in the front end, while troubleshooting JavaScript and HTML functionality. Key progress included simplifying the project layout, ensuring consistency in file paths, and discussing strategies to improve usability. We tackled challenges like debugging incorrect paths, clarifying how to serve misclassified images, and reorganizing files to streamline future development. Next steps will include finalizing the front-end functionality, testing thoroughly, and ensuring smooth deployment. Don't forget to explore Bionic Chaos at bionicchaos.com for more open-source biomedical tools. Feedback is always welcome, and we're excited to share these tools with the community. See you next time.
Bye.